Well, hello. Welcome to Living Web Farms. It's a nice cold evening. I'm, glad you braved the weather. I think it's supposed to get about 19 degrees tonight. My name is Richard Freudenberger. I am Living Web Farms Energy and Resource Coordinator. And what I do here is manage the renewable energy programs and workshops and things like that have to do with renewable energy or alternative energy on and around the farm. A lot of research into potential energy possibilities. We are strongly interested in biomass, solar, water management, wind. To some extent, you might have noticed we have a wind-driven water pumping mill outside at the entrance there. We have done some pond design and swale management, so we can collect rainwater and harvest the rain, collect it in large ponds, and then pump it, and then release it for irrigation and management. We have 3 different farm locations, so there's a lot of different things going on. One of the residences has a thermal solar system installed that we did a year or so ago. We have about 13, 14 kilowatts of solar power already at the Kimsey Road location, and just looking into more renewable and alternative methods and applications here for stuff on the farm. But tonight's class is more about, or is all about, low-tech human power. And it's not just bicycles. I mean, that's what people mostly think of is getting on a stationary bike or an adapted road bike that's been adapted to do a job. We're gonna talk about and look at opportunities for hand cranking things, pedal power. We'll talk a little bit about treadle power. I don't have a treadle power machine here, but that's an option for certain things, and I'll explain where that might be a good thing and where it might not be a good thing. We probably all have seen probably the most common application is a sewing machine, because it's not a particularly powerful driving mechanism. It doesn't need a lot of input, and that's another application, and we'll talk about this too, is where you need your hands free. You get a lot of power if you can use your hands and your feet, but if you have your hands busy, you can't do anything with them other than make power. So the point is to keep a steady pace and not wear yourself out too much. But what I really like to do is talk about what we can and can't do with human power, what types of jobs and appliances and whatever are practical and what is not practical. Talk a little bit about the energy of the human body. Talk more about, I think most people probably don't have a good background in like gear ratios and what that means. The size of the wheel, why is that one little and that one big, and why we even need to worry about that. We'll talk a little bit about chains, belts, direct drive. These are all the common methods for transferring power from the pedals or the treadle to the shaft that you want to drive things with. So I guess I should really ask out here, so I can sort of tune the discussion. What do people have any expectations of this hour and a half that we're going to be taking up here? As far as like what you want. Yeah.
I'd like to learn how to grind Char that I'm telling you.
Okay. All right. Well, this is probably very similar to that kind of a machine right here, so you're in luck with that. Before we had electricity and steam and all that stuff, we had to have human power. I mean, it was the only thing we had. So things like even a bow and arrow, I mean, that basically is a human-powered device. We had early on things like the potter's wheels. They weren't pedaled or anything like that, but they were just pushed along, and they developed a momentum, and then people could do their work. And grain winnowers and spring pole lathe. That's a spring pole lathe. This is a lathe here. This is something I had built many years ago. We had put this together out of wood parts and plumbing pieces. There's a wheel on the side here, and there's a string or a rope, which was probably vines in those days, or maybe hemp. So we have basically a stout string that goes up to a tree, a sapling that has a lot of, they hook the top of the sapling and yank it down so it bows down, and then attach the string to the wheel here, and they pull the thing down and it releases, and then pull it down and it releases, and so you don't have to continually worry about turning the shaft. The tree will do it most of the time. So that's another thing. And then a winnower is just a fan that separates the skin of grains like rice or wheat. Well, they actually have found wood cuttings in ancient China. I mean, a long time ago, of basically a rice cleaning operation where they had a wood cutting of a model in a rice room, and there was actually a little handle sticking out of the wall, and behind there was a fan, and it was a hand crank fan, and as the rice hulls were separated from the grain, the fan just blew the lightweight hulls. I have the dates written down on the sheet there. As we get into the 15th century and whatever, things were improved. Belt drive in the 13th century and treadle later in the 15th century. So, belt drive is basically somehow, whether it's an animal or a human, they're operating a treadmill of some type. And instead of having the equipment right there or being attached to that treadmill, there's a belt of some type, it's leather probably, reaching over and turning the shaft of something that needs to be operated. Spinning wheels are a real good example. It's a fairly ancient machine, and it's a treadle-powered machine. The feet only, so it leaves the hands free to do the work. Now, in the very earliest versions of a spinning wheel, there actually was somebody spinning the wheel because it's heavy enough to keep going. Spin the wheel, do a little work. Spin the wheel, do a little work. But once the treadle was developed, the wheel would continue to spin, and it does not take much effort. I have used a treadle sewing machine at home, and if it wasn't so heavy and bulky and snowing out here, I would have brought it here just to show you. But I'm sure you've all seen them in the antique shops and stuff. But it's basically a very simple operation, just like that, very slow. That wheel just goes around, and you develop a cadence, and it just, it's fine. You don't need speed. It doesn't require a lot of balance or technology or anything, really. So that's the wheel, and there's a little pin that comes out, and there's a wooden or metal shaft, and then there's a pedal. Like a big pedal, and another pivot, and then there's a rocker here. So basically you just step, this is out of scale, but you just step on the thing and it pulls the wheel down, turns the wheel, that moves down to here, this moves down to there, and then you use your heel to help encourage it to go around, and it's just jump, 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 and it really is a very slow thing. So then on here, we have a belt. It's a round leather belt like on my old sewing machine. It goes up to on the sewing machine, of course, it goes up, this goes all the way around, of course. And it turns a small pinion, which drives the feet of the sewing guts. This wheel goes around, but because of the large size of the wheel, the driving wheel, and the very small size of the driven wheel, that ends up going very quickly. And I'll talk a little bit later about ratios, but this is a fairly large step up if the wheel's that little. One complete motion of this wheel is going to make many motions of that wheel. Until the electric motor was developed, there was a lot of animal power, but there also was quite a bit of human power, and they took the form of either capstans, which are like a subway turnstile, or like in a ball game or something where you have to go through the turnstile with these arms that come out and a central shaft that's rotating. And so there'd be a person on each of those arms just walking in a circle, and not just one person, maybe four. If there's 4 arms, there's 4 people. And it's the equivalent of tying a mule or a donkey onto the end of one of those things and putting a carrot in front of him, and he'll just keep on going around. That was a pretty common form of punishment for debtors and other people who could be corrected, or who they felt could be corrected, and mostly in England during Puritan times. They weren't called work factories, but they were called improvement factories or something. But they would put people in large hamster wheels for doing things like grinding ore or wood chips or just whatever, and there'd be a huge hamster wheel, and the inmates would just walk and walk and walk and walk and just keep on going, and that was the way. And in America, we adopted some of it too, but it was a very brief period where that happened. I don't want to turn the class into a physics lesson, but you do need to know a little bit about watts, power, and time, and how it relates to work and all that kind of thing. The word horsepower is basically a derivative of pumps that they use to draw water out of mines in England. In northern England, there's a lot of coal mines, and when you dig into the earth, there's a lot of moisture, and as they have to pull the water out. In those days, they didn't have motors, so they had pumps that operated with horses on a mill or a turnstile. And obviously, if there were bigger horses or more horses, there was more power to be had. So when James Watt was basically the inventor of the steam engine, or at least the guy that actually first made it a practical machine that could replace the horses, he had to come up with a way to sell his product, and he couldn't really relate the the steam engine to the horse. I mean, there's really no way to have that connection. So what he did was just relate the ability of his motor to the ability of a horse. So if he had a 3 horsepower motor, that would be the equivalent to the mine owner that he has to go to, why am I spending 10,000 pounds on this thing? So it'll replace 3 horses. But actually, it was 3 ponies. That wasn't a good selling thing, so he just called it a horse. 1 horsepower is actually really closer to 0.8 of a horsepower. It's not a full horsepower, but that all comes about because of the pony and the horse and trying to sell this machine. So basically, a mine owner would know it's going to take me 3 horses or 3 ponies and this much grain and this much time and this much cleaning up of their manure and this much of a dying horse and then replace it with another horse and the investment over time. And that's that much money. And then here comes Mr. Watt with his steam engine, and it's going to require wood, but other than that, and water, of course, which is free. But other than that, it'll break once in a while, and we'll fix it, and it's not going to die. And it doesn't require, I can shut it down and not feed it, and all that. So it wasn't very long before the steam engine came into the realm over the horse. But that's where the word horsepower comes from, so it all relates back to the horse. There's a little chart here, weights and power potential of animals. And it just gives you an idea of the horse, and then you can see the oxen is not quite as powerful, and that's, it's a bigger animal, but it's not quite as powerful. The mule, the donkey, whatever. The human has 1/10 of a horsepower. Not a very good energy producer. That's why they use animals. Certain things that we may want to be doing with human power are not really practical for human application. There have been exercises and projects and studies and village-type endeavors where people will, in unison, take 10 people or 5 people or whatever. Then it makes it more practical. But that really takes a dedication and a labor situation, or like a university study where they just want to do a physics experiment or a applied science thing where you can say, okay, we're going to get 12 students. 1 student can generate this many watts of power and drive a little TV. We have 12 students can run 6 TVs with 36-inch screens and build a big long trestle thing and have everybody pedaling and give an example. I mean, I've seen things at energy fairs and shows where they will have demonstrations where they'll actually take people off or put people on and just show you how, by way of a digital meter, show you how much difference one person adding 1 or adding 2 can make in power output. This is a grinding machine, the lathe. This is a grain grinder we're working on. Small amounts of output electricity, and I'll explain that a little bit further, what the limitations are there. Fans, juicers, blenders, just a lot of that stuff, very easily accomplished if it's not too much of a high torque or high rotary energy input need. Yeah?
Do you know of any sources of converting the equipment? If you wanted to convert a blender or let's say something with a small electric motor like a dehumidifier.
I will tell you there are a couple of companies out there that do make like conversion, like pulley drive systems, or maybe they will pre-manufacture something for you that fits a certain Vitamix or a certain grain mill. I don't know what one of those common grain mills or something like a pulley kit or a like this here. Well, you can't really see it well, but in the back here, a driving system that inputs horizontally but outputs, so a right angle drive basically, and that kind of stuff. And it doesn't have to be necessarily for human power. I mean, you can, there's a company called, actually there is 2 companies I can think of. One is called American Science and Surplus. The other one is Burden Sales, which is actually the originator of Northern Tool and Hydraulics. There's a hydraulic division and then there's a mechanical transfer division, and it's mostly surplus. And it's not just big honking Caterpillar and John Deere stuff. They make little things. And if you really spend some time on the internet, I mean, we have to find things here. You'll find there's little places that just they bought 100 of some little device to, for whatever, it might have been made for something totally different, for a medical machine or for some kind of a press or something, and they're just selling them for very reasonable costs because they got them cheap and they're just making a little profit and they're passing them along. And they'll give you this total specs, what the input shaft size is, what the output is, what the horsepower was meant for, and you can sort of figure out if it's for your for your application or not. Again, I don't want to get into a physics lesson, but work is actually moving a weight 1 kilogram of weight, 2.2 pounds, 1 meter is like a Newton. And you'll hear the word, Newton and watt and joule and all this stuff, and I listed them all in there, but basically work occurs when you've actually, whatever force it takes to move that from here to here. Of course, if the weight is heavier, it's a different, they have to have a standard, so it's a 2.2 pounds. You move it from here to here, and it's a certain amount of work. When you add a time element in, then it becomes power. So 746 watts is equal to 1 horsepower, and that's something you actually can relate to, because like that motor might be a half a horsepower. So, the motors always have labels on them, tags on the side that will let you know what the watts are, what the amperage is, what the voltage is. Watts is volts times amps. That's just a very basic formula. You can get an idea if you're converting an electric appliance to a pedal appliance, you can get an idea immediately from the label what energy was required electrically to make that thing work. So if it says, you're going to need, you figure out you're going to need like a 3 horsepower motor to do the job or operate the appliance that you're looking at, like a pump or something. That's not going to happen with a single human. That's just too much. In the event that the appliance you're trying to operate is a very slow turning thing, so you don't really need a lot of speed, then it becomes a little more practical, because it's a lot of effort to pedal fast enough to make something else go fast enough. And when you step up the gears, like in this case, we have a small gear here and a large one there. So, for every single turn of that, every 1 revolution, that only has turned like 1/5 of a revolution, probably. When we talk about the ratios and stuff, we can explain that. But basically the size, the diameter of that wheel, of the driven wheel, and the diameter of the diameter of the driving wheel and the diameter of the driving wheel will determine the ratio. That can either be done in diameters, or it can be done in this case, the number of teeth. You can count the teeth on that one and count the teeth on that one and do your division, and you've got a 3-to-1 ratio or a 5-to-1 ratio or a 4.5-to-1 ratio. So in this direction, if we're driving it from, which we are from this side, it's easier to make the little wheel turn the big wheel. That's not going to spin as many times as this, so it's actually easier. If we're doing it the other way around, if we put that one on here, or if I put a hand crank on here, and I wanted to do it, I can hardly do it because I have to go through the flywheel and everything, but then that one would speed up quite a bit. So for every single turn of this one, that one might spin 5 times. I didn't count the teeth, but it's 4.5, 5, something like that. I can just see that. So that is a lot of effort, though. And you can say I think I can do it, but it's not easy. Of course, it's not easy because I don't have a crank. But this is nothing. I just get 2 fingers and it's done. So going in that direction, when you're going from a large to a small, it takes a lot of effort. Whereas going the other way, it takes a little bit of effort, but you sacrifice speed. The human body, like I said, we're about 1/10 of a horsepower. An athlete, and a well-trained athlete can do more than that, and also people can do short bursts, a minute or 3 minutes or 10 minutes, quite a bit, but they can't keep the pace up unless the job requires just a little bit of, burst of power. That's not really an ideal situation. For most of the things we want to do, we're just looking at a pace that you can actually maintain for extended period of time and be comfortable at it, and not exert yourself, because if you're exerting yourself too much, it's you're not really, there's no real benefit to it. If you're exhausted and you can't carry on the rest of the day. So ideal RPM is about 50 or so. It could be greater depending on the person. So that's revolutions per minute, so we can maintain that for quite a while. I guess the other thing too is that the way our muscles work, and it's a very involved subject, and you can read about it online or get a book about it. But the way our muscles work is we have enough energy stored in our muscles to basically just exert ourselves either quickly or strenuously or both very briefly. And basically that's an instinct that, we probably derived from caveman times where, you had to get out of the way of a mountain lion or a bear or something like that or whatever. So then after you've done that, sprinted away or threw the log out of your way so you could run or whatever it is you needed to do, you've used up that initial storage in your actual muscles. After that, a chemical reaction takes place and you're relying on the energy, the fat in your system and the sugars and starches that are basically go through a chemical conversion to feed the muscle, and that's a whole secondary process that occurs, and that's sort of what we do when we have to exert ourselves when we're running or bicycling or paddling or whatever we do. So it's that's what we're sort of looking at, and that's basically calories. I think it takes about 2,200 calories to maintain just walking around and doing stuff. When you look at the conversion of calories to watts, you can figure it looks pretty good. It's like we have about 100 watts available, but in a person, a little more than 100, which is great because that's great. I have a 100-watt generator. I can just do that. Well, it's not great because your body needs that too. I mean, you have to breathe. Your heart has to pump. You have to walk. Your digestion has to occur. Your blood has to flow through its veins. So that 105 or whatever 100 watts is being absorbed anyway all the time. So you don't have that much available really. So and the only way you can replenish it is to eat more. That's what the caloric intake is all about. If you eat more and you don't exercise, we know what happens then. If you exercise too much and you don't eat, we know what happens then. I mean, besides losing weight, you get exhausted, and at some point you have a failure. So, the whole point of the exercise is to keep our rotational cranking going at a nice 50 RPM pace or whatever, and in many cases we like to keep our hands free for doing the ancillary tasks that may come with the legs are the power and the hands are the job. So sewing, okay, so you're treadling and you're guiding the fabric through the stitches, or you're over here treadling for the lathe. This is up here at this level, and you're using the tool to run along this bar, and the wood is spinning here, and it's just chipping off pieces of wood while you go. So you have to have your hands free for doing the actual task at hand. Basically, the wood just goes in here between these two things. We tighten it up on it so it doesn't come loose, and then it spins, and we just run this sharp tool along the edge, and you can make shapes. You can make big balls on it, or just little curves, or spindle, or keep it straight, or whatever. But is able to form the shape of the wood as you want to. There's a lot of tools I didn't mention before. There's a lot of things we already have. Push mowers, grinding wheels. Meat grinders, post drill press. I see them still. People still use them. It's a huge drill press, which is a tool that you have a handle that actually drops a moving drill into a piece of wood or metal, and usually they're powered by motors. But before they had motors, they had it bolted onto a post, and you had a large hand crank and a big flywheel, and it just turned. You turned this thing and got this thing spinning, and then you put your work under the drill bit and pulled down this handle, and the drill bit went through the work, and by the time the hole was drilled, then it was time to crank again. And you could use two people if you had to. Somebody could crank and somebody could drill, but that was a very common tool. The push lawnmower, I still have one. I use it for little stuff. If you don't let the grass get too tall, it works great. It's not wet. And there's just a lot of tools we still use that are hand cranked. And this is some stuff I had at home. It's obviously old and whatever, but it's a meat grinder, and we can use it for a lot of different things, but sausage, stuffing, meat grinding, a lot of things. And that was just a small grinding wheel without electricity, just for honing The real reason I brought these was to explain ratios and things, and I can do that. But before we get into that, I want to start out with the drive systems, like the actual. We have chain drives, we have belt drives, we have direct drives. A friction drive, basically, the back of the bicycle just fits right into that thing, and the wheel is touching that. And then we take our chain off to drive the equipment that we need to drive. It's very simple. It doesn't require that you cut the bike up or take the bike apart. It can just, let me see if I can. So the bike, the back, usually they have axles that stick out enough so you can just drop it right in there. The back wheel touches on this. And of course, this has to be adjusted to the bike you're using. Basically just a friction drive. And as you pedal that bicycle, it drives that cog. It's simple, it's cheap, but it's not very efficient. And it's just because it's not really the inflation of the tire, how hard it's pushing against the drum here, or not, whether there's dirt on it, whether there's moisture on it, whether the tire has tread or not tread, or it's slick or grippy and new and squishy. All that affects the efficiency of the process. So as cheap as it is and as easy as it is to set it up, it's really not all that effective, and you're just losing a lot of your energy in this particular process, but it's still a good one. A direct drive, which is this, it's a straight, it's actually, you're very, very efficient because the only loss really is in the bearing here. I mean, this obviously is, it needs lubrication, but it's every turn, it's just one turn, and it directly does its job. There's a screw in there, and you can come up here and look when we're ready and see how it works, but it just jams. It's just a corkscrew that jams the meat out through a adjustable. You can replace these. You can replace these fittings here, so you can get different sizes, and you can adjust this. And then they have different sizes too, so you can get a larger cross section of meal through there. But it's a very simple device, and the corkscrew in there just once you mush the product in here, and it has to go out because there's no other place for it to go but that way. It forces it. So, but that's fairly efficient, but it's also very limited because it's only the one speed. If you want to go faster, you have to really go faster, and if you really need to go fast to do anything, it's not going to work. So. It'll work, but it's not going to. You'll never get up to the kind of RPMs you need to do some certain kinds of things. So we have another piece of equipment here, which is basically I would say that wheel is probably. This wheel is probably about 5 or 6 times bigger than the little wheel, so we're getting a lot of speed out of it. And so, that's pretty neat and very, very small. Portable, this basically is, this was in my grandpa's toolbox, one of my grandfathers, and he had, well actually it wasn't his, it was his father's. It was in his toolbox, but it was his father's stuff. And he's old enough that they didn't have electrical tools. I mean, in the journeyman's box, which is a very big wooden box that they had to build before they could even go out on the road, this was carried along in there because he had to sharpen his tools. He had chisels and other tools that had to be sharpened. So you weren't just going to walk up to the owner of the house or whatever and say, "Yeah, can I plug in?" I mean, it just doesn't, you had to carry your stuff with you. So that is a loss of efficiency, even though you're gaining in the speed, which is a good thing, but you're losing efficiency and effort in the friction between the gears and the heat that's built up. You're losing it in heat as you continually do this, it gets a little warm, and heat is just wasted energy. So, we're getting our work out of it, but it's you're losing a little bit of efficiency on that. A chain drive is really probably about the best system that we can come up with. It's a little more expensive than a belt drive, and I'll talk about belt drives in a minute, but the chain drive is, bicycles are all over the place. I mean, they're just not, I have just in working for this class here, I've just noticed them a lot more. I mean, there are free bicycles. There are really good bicycles that are $25. I mean, unless you're going out into racing bikes or some really, really nice off-road, trail bikes, you can get a very decent bicycle in various sizes and shapes, and ladies style, men's style, mountain bike, road bike, whatever, and for a lot less money than you might think. The cost is really reasonable, and the other thing is, with a properly lubricated and tensioned chain that is fit, perfectly, or as perfectly as you can get it, and aligned perfectly and all that, in the ideal world, a chain-driven system can be almost 98% efficient, which is like almost incredibly unbelievable. But with really good bearings, really good chain, perfect alignment, everything perfect. But even if it's not everything perfect, it's still an extremely efficient driving system, and it's a very positive system. There's no skipping. I mean, this is too long. There's actually a little tensioner that is part of this, but it's not. We're just fooling with this afternoon, so I didn't worry about it. But this, when the chain has to be set up correctly, it should be not too tight, but it should be fairly tight and well lubricated, and it's really important to match the chain to the sprocket, because there are there's actually two different widths of chain. By and large, the one size, the 3/32 size, is much more common, but there is still a slightly larger size for like track bikes that you might come across once in a while. So you don't want to put the wrong chain on, or the right chain on the wrong sprocket, or the wrong chain on the right sprocket. They have to be matched. And the only real thing is the distance between that center on each link. The rollers are on little pivots, little centers. So the distance between that and that's a half an inch, and the distance between that and that obviously is the same. If it's not, then it's not quite right. And the only other issue is the width of the sprocket itself. It should be a very tight. I mean, it'll wiggle a little bit, but it should be a fairly tight fit. And that's a certain width, diameter, or thickness, and the chain is a certain thickness, and they have to be matched up. So as I said, they do have 1/8 inch chain, which is a little bit wider, and that does not, even though it works, even though the half inch spacing is the same on both chains, you don't want to put the larger, wider chain on the narrower sprocket, because it's going to start to slop. And then once you start movement like that, or twisting, or even though it's not going to come off, it's losing energy. Any kind of unnecessary movement is going to be inefficiency. It's just all your efforts, not all of it, but a fraction of your effort is gone then. So, but again, chain is probably the best choice for almost everything you're going to do. A V-belt is another choice, and there is a V-belt on this side for the flywheel. Oh, that's a flat belt, but it's either going to be a flat belt or a V-belt. A flat belt has from the edge, like if you cut it a section of it out, the flat belt is going to be like this, and it has little ribs that go like that. Probably not that many of them, but I'm just overdoing it. But they, so it's a flat belt, and you've snipped it, and looking at it from the end, and there's on the wheel itself, there's ribs at each of these points. So the gripping, it actually helps to grip. It's a thin belt, and when we get up and look at this stuff later, you can look at it. But it's a thin belt, fairly flexible, and transfers power easily, and it bends easily. That's important. The other kind of belt is a V-belt, which we're all familiar with. The cars nowadays use a more modern belt like this, but the older style still used very, very common is a V-belt, looking at it from the end. And the pulley is then exactly shaped like that too. So you have contact surface in 3 places, one side, 2 sides, and the bottom. So, it transfers power very nicely without slipping. Yeah?
I've seen more and more usage of rubber combination cord drive belts to drive higher powered vehicles. And it's like the flat belt, only the ribs.
Or the other way, yeah. Okay, they're expensive. That's the only reason I didn't mention them. They are more costly, and there's no real need because we don't have the power like a motor does. They are designed for, to get that torque. I mean, they have to deal with that non-slipping thing. So their ribs are turned totally 90 degrees, and it's like a cog, and it grabs it. That's one thing. You don't really, for most of the human power stuff, you don't need that kind of torque ability. The other reason is that they are more costly, and and they bend good too. I mean, they have a nice bend. That's good too. They're flexible that way, and so is this. And this is a little less so, but it does have more, a little more gripping power, and they're also a lot cheaper, a lot more available. The V belts, and pulleys for them. All that stuff. Somebody else have a question? Or yeah.
This has a flywheel on it.
Yes.
And so could you explain the belt drive versus, and what is the other wheel?
Yeah, the pedals are directly tied in to the pulley that it has a V-belt on it that is driving this flywheel, which is about 10 pounds. But at the same time, it's also driving the input for the grinding machine. When you're on this thing, the most power you're going to get is at that position, because that's where your big leg muscle is shoving down on that. Now I have almost no power input because I don't have any. If I push down, nothing's going to happen. I'm already down, and if I push down on this side, nothing's going to happen because I'm already up. I mean, I can't go anyplace. But when I start to go here, this leg is now a big driving force. This less so because it's just a trailing leg. You can see with the pedal position, that's the least amount of power, and that's the most. So that ends up with a very squirrely, irregular power output or power input, depending on how you want to look at it. So the way to resolve that is to add the flywheel to carry that through, to carry those weak points through, and it'll just keep on. It has a stored inertia. Once you've got it up to speed and it reaches a certain RPM and it's going to carry that. It's going to level out those humps in that image that is in your handout. So we don't have to worry. It'll just carry past that point, and as long as you push and push and push, you're going to have you're going to have a fairly level power output through the whole thing. It does take power to start it. It takes more energy to start the flywheel, but once it's going, it's a real benefit, and it's especially good and especially necessary when you have a machine that requires a lot of torque, a lot of power, rotary power input, like a grinder or a pump or something like that, where you need a good supply of steady power without a jerky interruption to it. So this is about 10 pounds, maybe 8 or 10 pounds. Some of the potter's wheels, the homemade potter's wheels, and some of the other equipment I've seen pictures of anyway, they can be 80 and 100 pounds of like cast cement, just on a big bearing, a huge flywheel. And once you get that up to going and get it and really start spinning it, you basically just leave it alone for a while. I mean, it'll just keep on going, and but it does take the effort to get it up there. So it's really the kind of application. If you're just blowing a fan or something like that, that's not really a lot of input power, you probably don't need the flywheel. But if you're doing something like this, which, as I said later, we can all come up and look at it. But this has teeth in it. I don't know if you can. Well, you can't see it, but you will. It grabs. We have a material that goes in there, and then it hits that. And if we didn't have the flywheel, it might just stop it or slow it down substantially. We want that flywheel to carry that right past the problem and chew it up, and then and we'll just keep going with it. So that's basically it. It's stored inertia You can make them out of stuff that isn't meant to be a flywheel. This is actually a cast iron trolley wheel. Not a trolley, what do you call it, a dolly wheel? Like an industrial dolly wheel, and you can buy them like Grangers or, I mean, I see them all the time at either the flea market or the junk store, like especially industrial junk, like in the scrap yards. You'll see they're all rusted and everything, but you don't need it to be perfectly clean. They can be, the bearings usually can be knocked out and replaced, so that's, you know, if there's some money involved with that, that's, you know, that's that. You know, this is a very common size here, but you know, you can get a big, industrial fans and other bigger wheels, stuff like that. That's where they were never meant to be flywheels specifically, but they can be adapted for that. And actually, in a lot of applications, though, they were not only intended to be pulleys, but they were so heavy on purpose. They were made heavy on purpose so that they would act as a flywheel to help defray some of the energy going in. So, you know, that's basically, you know, that. Let me see. And they don't necessarily have to be, you know, that way. They can be flat too. They can be horizontal with the axis going vertically, and you know, like a potter's wheel. Yeah, yeah. And I can't think of a whole lot of things that you'd need that for, but there are, in drive systems, there are directional drives like that thing right here. So you're coming in this way and you're going out that way, or vice versa. And so you could put the flywheel either on the horizontal shaft or on the bottom shaft. Gear ratios, 3-to-1 ratio, or 5-to-1, or 6-to-1. Again, I think I went through this a little bit before. That's determined by dividing the diameter or the number of teeth of that gear into that gear and adjusting as you need to. In other words, if you have to go out and buy a bigger sprocket, then that's what is needed to be done. This fortunately this is a better quality bicycle, so these are removable. This stays, the center part stays, it's a hub, and then these bolts come off and you can easily take off this sprocket and replace it with a smaller one or a bigger one. And most of the better bicycles are like that. So you know, that's a good thing. You need to have the ratio knowledge because let's say you had a generator, an electrical generator, and that's what a lot of people think of a bicycle and a generator. It's really about 100 watts or so, 120 watts or something is about maximum amount of energy that you can operate, you know, with a pedal-powered device. I have seen, you know, 300 watt generators on these things, but the people can't keep up their pace with that. I mean, maybe an athlete can, but not for, you know, not forever. And some of those units also have battery storage. So basically, you're getting some hunky guy on there and just, oh, I'm going to sweat it out for 20 minutes and just charge that battery full. And you know, it is human power, but the battery is also carrying it, you know, quite a bit longer. So you don't have to, you know, it's not like you're watching TV off that thing and then you have to stop and the guy gets back on the bike again. I mean, it's basically a use of more than just mechanical power. So if you had a generator, for example, let's say an 80-watt generator that you're going to just light a little light bulb with, and you know that generator has to spin at, say, 1,000 RPM, because it says so right on there on the label, then you're going to have to figure out, if I'm spinning this at, say, 50, if I'm pedaling at 50, what's it going to take to get to 1,000 at this end? So, you know, you can either do a huge gear up here and a small one down there, or you can do a compound, which is also in your handout, where you go from one series of drives, you know, a big pulley here and a little one here, and then on the other side of the big pulley there's another little pulley. It goes up to another big pulley, so you're actually compounding the ratios as you go up. But you know, by dividing the number of teeth or the diameter of the sprocket or pulley, you can get the step-up ratio, which might be, say, 5-to-1. So I'm just using that as an example. If you're spinning 50 here, 5 times 50 is 250. That means you're going to have another 4 times up to get to the 1,000 you need up here. So you get an idea of what's going on. I mean, at some point it's just not really practical to spin something at 1,500 RPM or 3,000. Some of these motors, like that washing machine, I think it's a 2-speed. I think the upper speed may be, this is a washing machine motor on the end of this thing, which was maybe like upwards of 3,000 RPM. That's just not feasible in a human-powered device, because you're going to lose so much energy in the gear transitions, the compound gear transitions on your way up to that speed, that you're not going to be able to keep up your energy pace.
If you're grinding something like Char, which can be quite hard, it's
Right.
made from hardwood, then you would need to know how much power is required first,
Right.
before you worked it back to building.
Right. How would you do that?
How would you determine how much power?
What I would do is, it's purely empirical. What I would do is I would look for a electric device that did that, and that's going to also depend on how big the width of the thing is, because if you put it in a grinder that's only that wide, you're not going to grind that much, but it's going to be a lot easier to grind that. If you get a grinder that's, say, 24 inches wide, a hopper, it's going to take a lot more effort. So if the motor for that 24-inch hopper thing, which is going to be like that, is, say, a 1 horsepower motor, then you can extrapolate backwards and see how much power because I said a 1 horsepower motor is so many watts, 746 watts, so you know that you're going to have to output 7 times more than what your body can actually do to do that. So that's not possible. So what you'll have to do is either narrow the size of the hopper down to a reasonable width, so you're not feeding as much material in.
So your hopper can't be bigger than 1/10 of a horsepower.
The bigger you make your hopper, basically, which means the more char you're going to put in the hopper, the more horsepower you're going to need. So the only other way to resolve that problem is to go slower with it and use the gear ratio to transfer your leg power into torque at this size. So you'd have a little, just like this, you'd have a little gear here and a fairly large wheel up there. It's not going to grind the char very quickly, but it is going to chew it up. It's not going to stop you from doing it. It's not going to stop your legs. It's going to go through it. And I know we are grinding. We have ground wood and char and plastic and all sorts of stuff in here. So I know what it takes. And if you put too much in, if the rate of feed is too.
This arrangement here.
Yeah.
You have ground wood, plastic.
Well, not wood, not chunks. We haven't put that in there, but we put woody material like chips, and we put cardboard. This is a really heavy cardboard. That's a heavy wax cardboard box, and it's a substantial box. I mean, it's not an easy thing to chew up, and that's what we put here. And also plastic, pretty heavy, like laundry containers and stuff like that. But again, that's a very slow feed. It's not it's not something that you can just dump a 5-gallon bucket in there and whip through it. I mean, it's not that easy. So basically, by looking at your horsepower of your motor and keeping your eye on the smaller versions of those grinders, then you can get an idea of what it's going to take to feed into the system.
What about sourcing a grinder?
Like for this stuff, for char, we actually made this. I know that Dan, the guy who developed this thing, he had looked at commercial grinders, and basically they're very expensive, and so we basically just used the design from the teeth of that commercial grinder, and just had a machine shop laser cut us the shape of each of the teeth, and then we welded it onto a shaft and did it that way. But you can, I think, probably just looking around on some of the biochar websites and doing some research that way will give you some sourcing for grinding equipment for it. It's not just char. I mean, there's a lot of grinding needs for like a lot of things that are just as tough as char.
Now, there's a dust issue when you start grinding char too.
Yes, very much so. Yeah, and that's the thing. We want seal bearings here. So there's you not want the dust getting into your bearings. You don't want to breathe it. So if you're on the bicycle, you really have to wear some kind of a respirator, or even if it's just a simple, painting mask. Let me see. It's just keep your chains clean, because any kind of grit on the chain is going to eventually wear it down more quickly, and it's also going to reduce efficiency. So you want to make sure you're wiping. You get an oiled a rag like this and soak it in oil, and just take every once in a while just take and make sure it's getting clean.
Does the Char sufficient grit to wear the chain?
Yeah, over time, sure, because Char, it's it's soft. It's comparatively soft in the world of rocks, but it's not that soft. It's not like talcum or something. It's gritty, and it'll get into the pivots here. It just eats it. It'll just eat it up, and it's also a little acidic too. It's not. The surface of the metal eventually over time might get pitted if it's not oiled. Because if it's not oiled, it's going to adhere to the metal instead of adhering to the oil. The oil gets wiped off along with the Char, but if there's no oil on there, it's going to get into the surface. That's not good. So, and this is when I say wear, it's over time. It's not going to happen in a couple weeks. It's a long-term thing. Welding skills are not imperative, but they really are helpful. And you can get a cheap welder at, say, Harbor Freight, a very lightweight wire feed welder that you can master in probably 15 minutes to do this kind of stuff. They don't have to be pretty welds. It's not like a whole lot of stress on it. So you can replace a lot of this welding stuff with clamps, U-bolts, clamps, bolts, and stays, and just various types of things to do gripping work with. But a welder is actually really helpful. And the other thing that just a matter of stabilizing the bike. The bike frame is like, looking at it from the front. It goes like this, and the axle's here. It's not a very wide thing, so you're basically having to ideally put that on either a bar or a platform. This has a little short one. Now, when this was new, it had a much bigger one out here. We removed that, so there's a little short, leg that sticks out here. But in the front, we got this whole big machine. So that's stabilizing it. But when you get on something, especially as it's you're really pumping into it, and you're doing this, that bike's going to go like this, and when that bike goes like that, the chain goes like that. So you're losing energy in that. So that's just a matter of adapting. And when you're shopping for bicycles, you really do have a lot more choice than you might realize. If you spent a day, Saturday, just looking around at yard sales or whatever, you can see how many different seat heights and lengths and designs there are, bar placements, and then you have all the other stuff like the trainers and the stationary bicycles and all that kind of stuff. So that's something to not just grab your first one. Just spend some time looking and seeing what might adopt. A lot of people just put them on a big plywood platform and bolt them down, and so that way you really can't move them. They're pretty straight. Some people have staves that come out back here that actually clamp out there. So it might make it harder to get on and off, but it keeps it very stable. These are just like prototypes. We're not worried for this thing. We're not worried about. It's not supposed to be like that. We'll fix that. That's not a big deal.
That's just a traditional bike.
Yeah, that's just a regular old street bike.
That one at the bottom, it drives.
This was from a stationary bicycle, and this top part was from a regular bike. Like a regular street bike. Oh yeah. They're all bike stuff. It's all standard bike stuff. Oh, there's one other thing I really do want to cover, because I think it's a sort of a neat thing. This isn't finished, but this is actually a water pump. Whoops. Which I didn't put together. I used it, but I didn't put it together permanently because I wanted to show you. But I did not invent this. We had these things have been around for a while, but using PVC pipe and check valves and washers and just regular pipe fittings with no welding or anything really serious, you can actually manufacture a pump that, for about, whoops, they're not glued because I purposely didn't glue them because I wanted to show you the pieces. But you know, a very short stroke pump with rubber. You can either do it by hand, as part of your hand action. It has a T on the top. Do it that way, or with a lever. Or what I was doing was putting a collar around here and actually putting it onto a you know, like a treadle machine, but it would be hooked up to a crank like that, and then you would have your action. And I just want to show you, we're about ready to wrap up here. I just wanted to show you the, you know, this is basically put together out of old bike parts. That is what's called a Myers pump. It was a very common farm pump in its day, which is probably 30s, 40s, even into the 50s and early 60s. You can find them for maybe 50, probably more like 100, or if not, they're antiques now, so their value has gone up, and you can rebuild them. They manufacture that pump in Canada under a different name. That pump runs from $850 to $1,200 new now. But I can basically do almost as much with that $40 investment right there. So, you know, once we figure out the stroke and the stuff I was talking about here, that might be, and I guarantee you this is not going to last as long as that. It's going to have to be maintained more frequently and whatever, but at the price of, you know, a couple of washers and plastic pipe, it's worth it. The gaskets basically in this pump are just, you know, either rubber, EPDM rubber. We did some roofing work on this soldier fly house in the back, and I just cut rubber for the washers in there, and the or leather from my old boot. You know, cut a circle with a stout scissors, and then when it swells up, it gets soft. You put oil on it, it gets soft, and then it'll swell up and make a really good seal. So that's, you know, this whole thing is very, very low tech. And the most recent incarnation of this, I think, is called the Slapshot pump, and it's a company that's you can find it online. It's a company that actually provides parts and whatever for low-tech manufacture and repair in developing nations, and they send parts and advice and plans and whatever to places that need very low-tech stuff like villages. There's a better view of the pump itself. I think that pump was built in 1928, I think he told me. And they paid $100 for it, but it did have to be rebuilt. You can get a piston machine for that for quite a bit of money, or you can just use a roller skate wheel and clean it, and it fits right in and makes a piston. That's the kind of applied technology that, you know, we're interested in. I don't remember the gallons per minute that it does, but it's not a whole lot, but it's the equivalent of a regular household pump. He just goes up into this old pressure tank. This is not a bladder tank. This is just a regular old 80-gallon pressure tank from an industrial application somewhere, but he pumps water into that, and the air in the tank, there's a little bit of air in the top of that actually acts as the pressurization element. Pump 8 or 10 minutes, it takes care of a shower, most of the kitchen use, you know, that kind of thing, bathroom, wash your hands and everything. So maybe they only have to pump twice, maybe 3 times a day, 10 minutes at the most. And you know when to stop 8 or 10 minutes, because it just gets hard and you just get off, and that's plenty of water. He's off grid, so he's got, you know, he's got the batteries for the power for the house and everything. But I just wanted to show you also, that was a reproduction of a medieval human crane. I talked about people walking a treadmill where they get in there and hang on to these things in the middle so they don't fall off and walk, and there's a big spindle on the other side. You don't really see it, but there's a rope and a spindle, and as they walk, it just wraps that rope around that spindle, or capstan, and it lifts that arm up. This is the equipment they use to build those castles that you see. You'll see a castle in Austria or something on the top of a mountain. You've seen the Walt Disney type castle. You couldn't use a modern machine to get up there. I mean, you couldn't do that. They actually had to build this thing on the top of the mountain and lift those stones up, stone by stone, with something like that. And that's a small one. I mean, some of them are a lot bigger than that. But I just wanted to give you an idea of what can be done. That's a reproduction in the Netherlands. It was some kind of street fair they had. This is a lathe. Mark Dempsey is a consultant we use for our soil science. Occasionally he works here sometimes. He developed a pedal-powered lathe that actually works using both legs at the same time. I can answer questions later. We can look at this. I can show you what that's all about, whatever. But we're out of our official time. But I just want to thank you for coming, and hope we got what we needed to out of it.
Thank you.
Okay. Thank you. Yeah. Okay. Oh, sure. That's fine. All right.